So Nitinder is a senior researcher and the chair of connected mobility at TMU, Germany. His research interests are in the scale, edge computing, orchestration, next generation network system, and mobile environment, satellite networks, multipath communication, and others, and a wide scale internet measurements. He received his PhD from University of Helsinki, and his MTech from IT Delhi, and his PhD received his PhD dissertation received outstanding PhD dissertation award 2020 by IEEE Technical Committee of Scalable Computing. And he's the co-founder and co-organizer of different IEEE venues and ACM, like IEEE Prayerfield and ACM Leonet workshop. Nitinder, the
Right.
floor is yours.
Thank you. Thank you so much, Mohammed, for the introduction. All right. So today I will be talking about research that we have been conducting from the last year or so, trying to understand how Starlink network performance essentially looks like from different perspectives. But before I jump into sharing the results, let's first move into why we actually did this work that we are doing. So if you've been following this webinar, you must already be aware that we are entering into this era of LEO networking, Starlink being the front runner of this race with more than 4,000 operational satellites that are being deployed in orbits as of now. So it can provide really low latency communication and internet access to large parts of the globe. As of this moment, it is operational in 60 plus countries, but then there are new competitors that are following suit as well in recent times, in coming times. For example, Kuiper's is coming along, and then there are more companies. OneWeb is also coming along. But Starlink essentially serves as a role model of how those companies are going to work and what kind of latencies and performances we are going to be observing from these kind of networks. So first-hand accounts, since Starlink got launched in 2020, really shows super great performances from various parts of the globe, especially in regions that were previously inaccessible, in forested regions or in disaster-struck areas. Starlink really comes as a boon because you can get really great internet connectivity without having any terrestrial connection or endpoint deployed near to you. But while people have tried to look into how Starlink performance looks like from different perspectives, doing this from a global point of view is really challenging. And the challenge mostly comes from how Starlink is operating its network. So most of the Starlink dishes are deployed in multiple different orbits. These are primarily categorized into these three different divisions: the 53-degree orbit, the 70-degree orbit, and the 97.6-degree orbits. And the majority of the satellites are deployed in the 53-degree orbital shell here. What do I mean when I look into from this global perspective? Okay, this is just an angle that the satellites are revolving around. But when I make this flatter, you tend to see how the satellite coverage differs based on different geographical regions here. So this belt that I show in the red are the regions that lie within this 53-degree operational zone, which means that these regions are going to be seeing the maximum amount of satellites that Starlink has in orbits right now, close to 3,000 plus satellites. And the rest of the regions that do not lie within this belt will only be covered by satellites that are deployed under the 70-degree orbit and the 97.6-degree orbits. Which means that if you're doing any measurements, for example, from USA, which is covered by this 53-degree orbital belt, those measurements may not directly equate to your performance in, for example, Sweden, which doesn't lie in 53-degree orbit and needs to connect to 70-degree satellites. So this really creates a problem about how do we actually assess, from a global point of view, the impact of these different orbital shells on end-to-end performances. Second is the way Starlink actually gets you connectivity to the internet. As of now, the Starlink follows pretty much like a bent pipe model. And this has been discussed extensively within this webinar series as well. What do I mean when I say a bent pipe model? It essentially means that when you have a Starlink dish, the Starlink dish connects to a satellite which is in its field of view. And there are multiple ways that it can connect to whatever satellite it wants to connect to. But then that satellite routes your connection down to the nearest ground station. Now, this looks like a bent pipe model because this essentially makes your Starlink connect directly to the ground station, which then gets you to a point of presence that connects you to the outside internet. Traditionally, this was thought of that this bent pipe connectivity is just a single hop link, which involves only a single satellite. But Starlink has come across and has publicly announced that it has been using inter-satellite links as well, which means that these satellites themselves may be connected by these laser links. And so rather than going directly via this one hop, you may traverse multiple laser hops before you get to the nearest ground station. Uh, this looks all really fun and dandy, and this is absolutely necessary for getting you access to those really far off remote regions. But the issue is that these satellites are moving at very high speed. So they're moving at 27,000 kilometers per hour, which means that those links are actually very, very dynamic. And your connection between your terminal to the nearest dish can change very frequently. And this creates a lot of problem. There have been some studies about how this impacts end-to-end performance, but a lot more information is necessary, and especially from a global point of view. So this is essentially what we did. So in this talk, I'll be sharing the results that we have in this particular paper, which recently got accepted in the ACM Web Conference. The presentation for that will be in 2 months in Singapore. And this work was done in collaboration with my colleagues in Technical University of Munich and the University of Edinburgh. All right, so let's jump into it. So the first thing we wanted to do was to understand the global perspective on how the global performance of Starlink looks like. There are a couple of ways to do this. One is that, okay, you deploy your dishes all over the globe and you actually do measurements from those control dishes. And this is what, for example, efforts like LeoScope intends to do, which you will probably hear about this later in the webinar as well. What we employed was a different perspective. So we ended up doing passive measurements of passive analysis of measurements that have already been conducted by Starlink users globally. More specifically, we relied on this measurement labs speed tests. What are measurement labs, if you're not familiar? So these are kind of like Ookla speed tests, but MLab is operated and owned by Google, which means that if you search for speed tests, for example, on google.com, or you go to MLab website, you will be doing your measurements, both the downlink measurements and uplink measurements, and also the speed test, your latency measurements to this MLab server, which is to the nearest Google Cloud Data Center. The good thing about MLab is that all of the measurements is completely open source. So we actually looked into it. We filtered for all measurements that were done by users of Starlink. And in the end, we got about 19.2 million measurements from 34 different countries. And these were very statistically significant results since the beginning of 2021. Now, the issue with MLab measurements was that these are only end-to-end measurements, so we do not get a breakdown of performance numbers, especially if you want to look into last mile performances. So for that, we actually did active measurements over IP Atlas platform as well. And we ended up selecting about 98 different Starlink probes that were connected to RIPE Atlas platform for 21 different countries. And our endpoints were about 145 different data centers from 7 different cloud providers. And these 7 different cloud operators had Google, Microsoft, Amazon, Alibaba, Linode. So we were not really dependent upon just a Google data center in this case. All right. So what does the performance essentially looks like? So in this slide, you will see a side-by-side comparison of the Starlink performances from a global point of view compared to the top 3 mobile network operators within that particular region. You will see that these latency numbers that you see here, these are median latencies end to end that the users observed towards the MLab server. So what we see is that for Starlink, the median latencies as of October 2023, when we actually finished our analysis, this was around 40 to 50 milliseconds or so. Mobile network latencies, the competitive ones within those regions, they were a tad bit lower. So you could see approximately 30 to 40 milliseconds latency. And this kind of raised the debate that, okay, is Starlink really better than cellular or not? But we'll get to that later. What we also see interestingly here is that a couple of regions actually enjoy really good latencies. For example, the US and parts of Europe, they see latencies less than 40 milliseconds, closer to 30 milliseconds or so. And I will also get to that later. Why do they observe these latencies on, whereas the regions, for example, in South America or in lower parts of Africa, they do not get to see that. But what we essentially can see from this graph is that there are no specific regions where Starlink is completely outperforming cellular as of this moment. But that is something that can also be debated because cellular may not be accessible in those remote regions which requires significant amount of base station deployment. But Starlink, you just need to put up your dish and you can actually get access to the internet. So there are two sides to this particular coin. But if we dig in a little bit deeper about how the latencies look like, we start to see something interesting emerge here. So the plot in the middle, in the lower half, let me actually put up my laser pointer here. So this plot here shows actually the deployment of your ground stations and the point of presence that Starlink has deployed for connecting users to the local internet. So ground stations are these brown circles, and the point of presence are these blue triangles here. And what we see is that the regions that have very high deployment of ground stations and POPs, they tend to get much better performances. And this is what you observe, for example, in US and also in Europe. Regions that do not have that good number of ground infrastructure, they tend to have a longer performances here. For example, Mexico City, and then you also have Manila, the Philippines here, which only has a ground station locally. If I dig into a little bit deeper, it seems one interesting bit that we also observed was that regardless of wherever you're connecting within US to a Starlink, your latency structure and performances are very, very consistent. You will see almost similar amount of latencies just because there is a lot of ground infrastructure and POPs available to put you to the nearest internet endpoint. In Europe, you have only 3 different POPs available. You have one in UK, you have in Germany, and you have in Spain. This was again in October 2023. So you saw, for example, Italy that connected to a POP in Spain, it had a larger latency trend compared to, for example, Germany, which was connecting to a local POP that was deployed in Frankfurt. And then in South America, you tend to see a significantly higher latencies. In almost most of this, your median latencies lies between 50 milliseconds all the way up to 100 milliseconds or so. This was a little bit better, for example, for Brazil, which actually had a POP and a large amount of ground station availability. But for other regions, these availabilities are a tad bit lower, so the latencies are a bit higher as well. But these are the latencies that you might observe when you're making a connection. One other thing that Starlink actually has been notorious about is suffering from buffer bloat. Now, if you're not familiar with buffer bloat means that when you're making an active transfer on a particular link, your queues on that particular link gets bloated because it's still serving the packets that to the endpoint. And if you do not do a good amount of, you do not use an algorithm which can actually do your queue management well, you will end up having a large latency, especially during an active transfer, both in uplink and downlink. So this is what we essentially looked at. We looked into what is the RTT inflation that users can see while the test is ongoing. And we observed that in Starlink, there is definitely buffer load because the RTT inflation goes all the way up to 250 milliseconds, even 300 milliseconds, especially during download. So it increases by 2 to 4 times. This seems to be a bit better during the upload when the dish is uploading data, for example, to a remote endpoint. So this is sending the data to the satellite versus downloading the data from the satellite. And in this case, we kind of hypothesize that it might be that Starlink is using some sort of active queuing mechanism in its local satellite dish. But we'll explore that later as well, because Starlink came out with a public notice very recently where they kind of accepted that, yeah, they have been doing something very similar. All right, so this gives you a good idea about how the end-to-end latencies can look like and what factors are affecting performances of Starlink. I want to bring your focus to this 2 very peculiar use cases that we observed in our measurements. So first was in Philippines. The interesting bit here was that before May 2023, any Starlink user from Philippines connected to its local ground station that was also deployed in the country, but then the nearest POP that it could connect to was in Japan. So it means that anything that you are trying to connect to the outside internet first needs to traverse over this long Jupiter subsea cable before it ended up going to your endpoint. And this is what we see, for example, in this map, in this plot here, which shows that, okay, if you're connecting from a Philippines client to a server in Japan, you tend to see a much lower latencies versus if you were to connecting to a Philippines server, because then the packets are coming back via the subsea cable to the country and connecting to the server. But what happened was that after May 2023, Starlink actually also deployed a POP in the country as well. So what we started to see was the trend inversed completely. So after May 2023, you had significantly lower latencies to connect to in-country data center, in-country servers, versus if you were going over to Japan, you had to traverse this long link, which added up this additional cost of latency. So this kind of shows the importance of why Starlink wants to deploy more and more ground infrastructure to get you to the faster internet much quickly as possible. But then on the other side of the coin, we also wanted to see what is the impact of the intersatellite link. And assessing this was very difficult because these links between your dish to your ground station, you do not see this on your trace route. So these are all tunneled links, which means that you can only make educated guesses. What we saw was that, okay, this dish that were deployed in Reunion Island, which is the small dot here in the south of Africa, this was connecting to a POP which was deployed in Germany. So this was very peculiar to us. So we wanted to first understand, okay, if probably this Reunion Island dish is connecting to some ground station in Africa, and then it's using the terrestrial links to get to Germany. So we looked into what is the latency between the ground station and the POP here. And we saw that, okay, the ground station and the POP latency is less than 5 milliseconds, which means that this dish is using a ground station which is also deployed near Germany. So it's not using anything near Africa. And if you look into the distance between these two endpoints, it is close to 9,000 kilometers. And the range of one satellite is closer to 1,200 kilometers because it's flying at 500 kilometers altitude. So it definitely cannot be connected by a single satellite link, which means that it is definitely using some inter-satellite links to connect to that ground station. And with that in mind, we actually tried to break this up. And this plot here actually shows a couple of things. So number one, it is showing what is the latency from this Reunion Island dish between the dish and the ground station, and then also the ground station and the POP. And then we also did parallel measurements. We also found data from Germany, the Starlink dish in Germany, where we also plot the latency components from these two aspects as well. And you see that the ground station and POP latencies are similar for both, which means that they're likely using the same ground station as well. But you see that these are using a significantly higher ground station dish. Your intersatellite links consume a significantly higher latency, especially from the space lasers. What we also plot in this vertical lines are probes which are connected in Reunion Islands, but they are connecting to this Germany data center via fiber link. And then this is the probe which is connecting to Germany and connecting to this Germany data center via the fiber link. And what we see here is that intersatellite links actually get significant improvement compared to terrestrial links, especially when they're traversing these long distances. And the major reason why is that because the Reunion Island is really offshore. So it traverses multiple subsea cables before it gets to the European IXP and it gets to Germany. And this routing inefficiencies actually add a significant latency overheads. Starlink kind of avoids that and gets a much lower latencies end-to-end. All right. So this was the global analysis that we did. We also did application performance measurements. So we looked into two major applications. One was this Zoom video conferencing and the other one was cloud gaming. And we did measurements comparing Starlink to Ethernet and 5G connectivity from different regions. I'm not going to go deeper into the results, but mostly going to share the overview summaries here. What we found was that Starlink in our application-based measurements also performed very similar to the non-standalone 5G deployments, achieving similar amounts of latencies, achieving similar amount of packet losses as well. It is also comparable to terrestrial fiber in some cases, but the latencies are a lot more variable and there is a lot more packet losses as well. So this is something that you will have to keep into mind if you're running anything which desires ultra low latencies over Starlink. The interesting bit that we wanted to, that we observed when we were doing our measurements, that actually at finer granularity, we saw very periodic degradation in application performances, both for Zoom as well as for your cloud gaming. So this was largely absent in terrestrial networks. In 5G, this only happened when you were doing handovers. But in Starlink, this happened regardless of wherever we were connecting it from. And this happened almost every 15 seconds marker. And there has been a lot of work being done in this space. People have alluded that, okay, this 15 seconds things, these reconfiguration periods exist. And what Starlink possibly might be doing is it's using a global network scheduler that reassigns your satellites to these dishes every 15 seconds or so. We also did measurements from dishes in Germany and Scotland, where we ran iPerf as well as we ran IRTT, and we found that, okay, both for downlink and uplink, there is degradation that happens at the intervals of these 15 seconds, especially at the envelope. So this does exist, but we wanted to understand if there is actually a scheduler that is reassigning dishes to the satellites to these dishes at these periodic intervals or not. So for that, we first wanted to do we did some measurements from, like I mentioned, from Scotland and Germany. So these two are very far away from each other, and they're connecting to both different ground stations and POPs. So you do not have any overlap of which satellites are going to be providing connectivity to these two dishes here. And what we do observe is that these 15 seconds reconfigurations are prevalent in all locations regardless. And the interesting bit is that these 15 second intervals are absolute time synchronized. So these occur at the absolute time value of the clock. At the envelopes of these, like I already mentioned, throughput and RTT fluctuates, but within this, it remains relatively stable. So the idea was, okay, maybe it is absolutely true that Starlink is doing satellite handovers every 15 seconds or so. And people have tried to look into this and have tried to come up with some sort of takeaways here by using, for example, obstruction maps, and then making educated guesses if your dish has changed your satellite or not. But this is very difficult for most of the globe, because if you are in this 53-degree orbit, you are covered by close to 15 to 20 satellites at any given point of time, which makes it very hard for you to make a guess that, okay, now your dish has made a shift between this 115-second period to the next 15 seconds period. So what we did was we focused on this dish in Scotland, because this was placed above the 53-degree horizon. So, and this was mostly covered by your 70-degree and 97.6-degree orbits. So we actually put a metal shielding on the southern side of the dish so that it is restricted from the 53-degree orbit satellites. And we verified this from the TLE and the Celestrak data that, okay, based on when the dish is getting connectivity, is it getting connectivity from a Starlink dish, which is in the 70-degree or the 97.6-degree orbit or not? And this is easier to do because these orbits are very sparse, and you only have 1 to 2 candidates at any given point of time. And most of the time, you do not even have any candidate at all. So you end up getting no connectivity. So we got some super interesting results. So number one was that we saw that in 2 periods, which is this plot here, the dish was getting connectivity from the same satellite, because it could not, there was no other satellite in the orbit at that point of time. But we did see a shift in latency occur at 15 seconds origin. So it's not that, so our hypothesis here is that Starlink is not really doing a handover at the 15 seconds, but it's likely doing some load balancing as well, where it is doing some reconfiguration of your links. What we also observe is that, especially looking at our periods when we were not getting any connectivity during the 15 seconds period, we saw that we lost connectivity always at the envelope at the start of the next 15 seconds period. So Starlink kept connectivity until the very end, but maybe it looks into the satellite candidate availability list and then it doesn't find a satellite, so it loses connectivity. So you do not see connectivity at all. But whenever we try to kickstart the dish again, the connectivity starts at any given point of time. So it seems like the algorithm that Starlink is using internally is that get connectivity as fast as possible, but wait until the reconfiguration period before you need to make a shift to another satellite or not. Okay, and that brings me to the end of my presentation today. To summarize, Starlink does appear very revolutionary from a global perspective, and the performance seems to be extremely competitive to the current cellular network that we have deployed most of the time. Plus, it provides an additional benefit that connect to these underconnected and provisioned regions due to ISLs. We see a shift a split in the Starlink philosophy here, because in one way they are deploying more ground infrastructure to get you to the nearest terrestrial endpoint. On the other hand, they can actually maximize the use of the ISLs to actually get connectivity from these remote regions. How Starlink seems to be doing this internally, it's a bit unclear, but this seems to be a thing that they are figuring out still. An interesting due course that I wanted to talk about very briefly, if time permits, is that we released essentially this study and all the problems and bottlenecks that Starlink is observing on archive in October 2023. And Starlink essentially a couple of weeks ago published a circular where they talked about that they have reduced a lot of these issues that are prevalent within their networks. And this was based on the work that they essentially did starting from November to Jan. So we actually looked into what the circular was. If you want to also read it, you can go to this link. But to just give you a summary, the claimed improvement was that, okay, they wanted to reduce so they have reduced the last mile latencies, which we were observing between 40 to 50 milliseconds, closer to 30 milliseconds. And the way they're doing this is by optimizing the front haul wireless use. They're also reducing the median latency for most of the globe by adding 6 new POPs. And an interesting bit was that they actually reduced Bufferbloat. And the way they did this is by resizing the buffers on the path end to end. And in this document, essentially, they also alluded to that they're using some sort of active queuing mechanism as well. An additional bit that they also released, which was pretty cool, was if you go to this website, you can actually see what kind of latencies they claim you will be getting if you're from different parts of the globe. So you will see that most of the latencies are likely between 25 milliseconds to 75 milliseconds or so. So this is just a claim, and we wanted to actually understand if this claim performance is transferable to what we also observe. So we did very, very quick analysis. So this two plots essentially shows the last mile latencies, which is the latency to your ground station and your dish from different parts of the globe in September, October 2023, and then in the last 3 weeks, essentially. And we do observe that, okay, they have reduced their latencies by 5 to 10 milliseconds in most of the cases, especially Canada and parts of Europe, which were lying within this 40 to 50 milliseconds buffer bucket, now have jumped into this 30 to 40 milliseconds bucket. So there are good signs here. But for regions which are using ISLs, especially this Virgin Island use case and this Reunion Island use cases, where it's very likely that they're using ISLs, we do not see much improvement here. But what I wanted to add here is that this is just a very quick analysis, and more comprehensive analysis is required in this space. But kudos to Starlink for actually listening to all the research community and improving the network operations. Okay, and that brings me to the end. So if you want to read the paper, you can follow these QR codes. Our code and the data sets is all public as well. Just to mention very quickly, we are also doing new measurements where we want to look into the CDN performances and the circumvention that Starlink allows you to do. And so we launched this browser plugin called NetMed. If you're using Chromium, you can follow this QR code and download this plugin, which actually does measurements using MLab and your CloudFront CDN. So I would really request you to do that. And I'm happy to take any questions.